So we're on the air, I guess. Okay, first of all, homework 1 is due Thursday, so now's the time to ask questions about it. Any questions? Some people have been emailing me questions about programming, and most of the time I can't answer those questions, and even if I could, they're too complicated usually to write an email. So now's the time to ask those kind of questions, because if you're asking a question about any particular operating system or something like that, any technical details, somebody here might know. So are there any questions about BASIC? What you're supposed to do is put it in another loop, or inside a loop that says for next. So for example, if J is the index that you're looping on, if at the very top you write for J equals 1 to, say, 10,000 in your case, and then at the bottom you write next J, then everything in between those two instructions will loop as many times as instructed. In this case it would be 10,000 times. So the only changes you have to make if you're using BASIC is you put it in a loop that fixes the number of iterations. And the other is that you only want to print out the values indicated in the table. So that means you need to have some instructions which say print only if this is true. There are different ways to do that. The simplest way is to just say if J equals 1, then print whatever it is you want to print. And if J equals 2, I think there's about 8 different times you have to do that. So it's not very elegant, because you've got to write the same stupid thing 8 times, but it doesn't take very long. It's easy enough.
I was using the do until statement, and it shows in one of those tutorials, do until you put all the stuff inside, and after that you put loop to end it all. For some reason it was not on. I was the guy who emailed you the QBasic, and for some reason it was not stopping at loop. So I put an end statement, and that sort of put an end.
That made it work?
Yeah.
Okay. Whatever works for you, then we're going to be doing this over and over again.
You're not going to be too picky on the code.
I don't care about the code.
Oh, okay.
As long as the logic is correct, that's all I care about.
Okay.
Otherwise, you can use a completely different language. The reason I use BASIC is because it's easy, because it's a good pseudocode. You can see the structure and the logic from what I write down. And it doesn't have any overhead associated with it. You don't have to define your variables. It knows what's an integer, what's fixed, and what's floating, that kind of thing, without your having to specify. So you just concentrate on the logic. Anything else on that? So it should all be working out just as predicted, right?
Yeah.
Yeah? Okay. Okay, so the next thing I want to do is I want to talk about homework 0. And I haven't given a due date on that, roughly 3 weeks. Let's see how much I get done today. Maybe I can do the whole thing. This is the mathematics review. And it's homework 0 because it's really not related to the course. That's why I started with the 0. It's a prerequisite material. But it's very important. You have to know it. But you don't have to know it right away. So what you should do is, if you don't know it now, learn it between now and roughly after the midterm, approximately a third of the way through the course, because we're not going to use this stuff until about a third of the way through the course. Okay, so what homework 0? First you should download it, and there's usual a statement and a table which you're going to fill in on the bottom. And then also you're supposed to download some graph paper. And I want you to use the graph paper, this graph paper, so everybody is using exactly the same scale. Now I'm going to make a change in the statement of the homework. I'll explain it as we go along. So what that means is that the version that's on the website now is not the final version, so there'll be a minor change. But what you should do is, of course, do everything on scratch paper, and then do all your calculations on separate paper, and then at the end you clip together, staple in the upper left-hand corner, the cover sheet and your graphs, and then whatever calculations you use to support it. And this is a little bit different from all the other homeworks in that it doesn't require any computer. Although you have to do some integration, and you could do that using a computer. Like you can use mathematical software like Mathematica or Maple, and you should also use, or could use, a calculator like a TI-89, which is a good thing to have. And as I said, if it were me and I had a choice between buying a book or buying a good calculator, and I could only buy one, in this case I would buy the calculator. Not that you'll use it more in this course, but calculator should be for a long time. The book at the end of the course, most people want to sell it anyhow. And besides that, the book will be on reserve. I think it is on reserve in the library, so you can always go to the library. Okay, so are there any questions before I start talking about homework 0? Now, as it stands, homework 0 is just a math problem, but it's totally based on, motivated on applications that are going to come later on in the course. So as I go through it now, I'll try and explain what those things are, but that's just sort of background material. Don't worry about it. Don't worry about remembering it, because it'll make sense in detail later when we're driven by the application. Now it's just a question of getting the technical tools out of the way, so when the application comes by, then you can concentrate on that. So it says a random variable x can be described by its density function, little f, or its distribution function, big F, and they're related as follows. So these are definitions. So there's something called the density function, little f sub x of t. And the little f, that means it's a density function, whatever that means. The subscript x tells you what random variable it applies to, and t is a dummy variable or independent variable. And the density function is a function that describes the randomness of the random variable x. So later on, we'll discuss the specific x's, although there are 2 examples here, and how the little f describes the randomness. But for now, it's just a function. And the way, one definition of it, if it's the derivative of another function called the big F, and that's called the distribution function. So one thing is you have to make sure that you can write clearly and differentiate between uppercase f and lowercase f. And they both have the subscript x, which means they refer to the random variable x. So you can describe a random variable either by its density function or its distribution function. And if you know one, then you can get the other. So they're equivalent descriptions of the same thing. So the first statement says that you get the density function by taking the derivative of the distribution function. Now, you can go backwards, and you can find the distribution function by integrating the density function. In fact, the distribution function is the area under the density function curve between minus infinity and t. So what this says is, take this function little f and find the area under little f as the dummy variable u varies between minus infinity and t. And this t is the same as that t. So this is very important. And this is, in fact, basically the fundamental theorem of calculus. It's the relationship between derivatives and integrals. So if I told you little f, you could get big F by performing this integration. And if I told you big F, you could get little f by differentiating. And of course, by what's called Leibniz rule, which is what you learned in freshman calculus, if I took the derivative of this thing right here, then writing the derivative of this, in effect, just takes this upper limit and puts it inside the function right here. So the derivative of an integral with respect to its upper limit is simply the integrand evaluated at the upper limit. So if I took the derivative of that is, I took the derivative of that, I would simply take the t and put it down in here. So we'll go through examples of this, but this is stuff you're supposed to know from calculus. In fact, this is the essence of calculus. Because in calculus, what you learn is you learn about differentiation and integration. The trouble is that in most calculus courses, in many calculus courses, the emphasis is put on actually how you make the calculation, and those calculations can be difficult because basically what you have to do in order to evaluate an integral is you have to find a function whose derivative is the integrand. So you got to work backwards, and that can be very tricky. So there are lots of tricks like integration by parts and making trigonometric substitutions, things like that, which help you evaluate the integral but have really nothing to do with the meaning of the integral. So in our case, except for one minor part where we integrate by parts, the details of integration, of actually calculating the integral, are almost nothing, because we're only going to look at the simplest functions. The important thing is understanding what these things mean. Okay, so for now, take my word for it that big F and little f describe the randomness in a random variable. Now, once you know those things, either of them, of course, when you know one of them, you know the other one. Once you know them, then you can calculate all of the measures that relate to the randomness. For example, you can calculate what's called the expected value, which is called E of x. And E of x, or expected value, corresponds to the mathematical idealization of average. So what we'll want to do in the future is, given a random variable, we'll find its density function, and then going to put it in this formula, evaluate the integral, and that'll tell you what the long-run average of that random variable would be. And then later on, we'll actually check that by generating these random variables in the computer by simulation, and then calculating the average and comparing that with the expected value. But here's the way you calculate the definition of the average. You take the dummy variable, you multiply it by the density function, and then you integrate that over all possible values of t. So I give you a little f, you put it in here, you turn the crank, and you get an answer. Then there's something, this is sometimes called the first moment, by the way. And then there's something that's called the second moment. And the second moment is something that's harder to explain in terms of what it means right now. Let's just say it relates to how variable the random variable is. And the definition of that is it's the average value of the square of the values that the random variable takes. So it's the same kind of thing I integrate between minus and plus infinity. And then finally, there's something called convolution, which I'm going to call g of t here. And g of t is given by the following integral. You take f sub x of u, f sub x of t minus u, du, and you integrate over all u between minus and plus infinity. And again, that t is the same as that t, and this u here is the dummy variable, and you're integrating with respect to u. So when I put these functions in here and integrate, then the u goes away, and the answer has only a t in it, and that t is the same as that t. So one of the things that students have a lot of trouble with, same thing you see over here, is they confuse the dummy variable, that is the index of summation, with the variable of the function, that is that t and that t. So this integral is a function of its upper limit. And similarly, this integral is a function of that value there. So when I write this integral, I could call this u, I could call that y, and that dy, or x, and dx. But I cannot call it t, because if I put a t in there, and I put a t in here, of course, that wouldn't make any sense. And the answer, the result is that that t, which is not correct, but if it were a t, it would be confused with that t. And of course, they're different. So this is one of the traps that you'll have to watch out for. Same thing over here. I can call this variable right here anything except t, because I'm going to use this t for that t, then this thing can be anything except t. I could call that u du, x dx, y dy, but I can't write t dt. Of course, what a lot of people do is they write t dt, then they get the right answer, but they get the right answer because they're not actually evaluating the integral according to the rules. They're sort of doing it in their head. That's the way students tend to do things is you're taught some complicated algorithm or rules for doing something, and then you find a shortcut that works, and then you use the shortcut, and if you get the same answer in the back of the book, you don't worry about it, and you go on to the next problem. But in all of the elementary exercises where the emphasis is on the tricks of integration rather than the meaning of it, it doesn't make any difference. But here, the emphasis is on the meaning of it and not on the tricks of integration, so it'll make a lot of difference. So it's important then to understand what this stuff means. Okay, now, what we'll see later, although it doesn't make any difference at this point, is remember that these density functions, these represent the randomness in a random variable. And if I had two random variables and I wanted to add them up, then the result would also be a random variable, and it would have some randomness. And this formula, which is called a convolution, calculates the density function of a sum of random variables in terms of the density functions of the random variables themselves. So this will turn out to be very important later on in the course, but for now it's just a formula. So let me write down that the hot word here is called convolution. This stuff, this notion of convolution is very important, not just in probability, but in other areas as well. Like electrical engineers are probably familiar with it, used in signal processing. So there are always students who go to the web and they look up the word convolution and they get tons of stuff which they download, and then they get very confused. You can do that if you want. You can look at any book that you want, but I don't recommend it. My recommendation is just follow the rules that are taught in the course and don't confuse yourself. So I think that if you look this up, the only good part of it is you'll see that I'm not making this up, that it's everywhere, but I don't think it would actually be helpful in understanding how to evaluate or interpret them. So the statement of the problem says, later these formulas will be given physical interpretations, but for now take the viewpoint that the following exercise will get the mathematical details out of the way so that later we can concentrate on their meaning rather than their calculation. Then it says fill in the following table. So I'll write down a table. You have that in front of you. Show all work on separate pages. Draw the graphs of little f, big F, and G on the graph paper provided. So you can download the graph paper, and as I say, in this case I want you to use this graph paper so everybody will have the same scale, and it forces you to do it by hand. But later, you can use any scale that you want, any graph paper. The best thing, if you know how to do it, is have the software draw the graphs for you. But on the first one, I want you to draw the graphs. And then it says there are two parameters here, A and B, and it asks you to evaluate some things. So before we move on, everything makes sense so far? Okay, so all I'm going to do now is I'm going to take two particular functions, which happen to be important in probability, and I'm going to put them in these formulas, or ask you to put them in these formulas and derive them. Okay, so here is the table that you're going to have. There's going to be two f's. I'll start writing here. So the first one is given by the following formula. It's 0 when t is negative. It's 1 when t lies between 0 and 1. And it's 0 when t is greater than 1. So this is like the world's simplest formula, simplest function. If you draw the graph of it, one of the things I'm asking you to do, and by the way, the way this works is most of this I'll do right here. But the details I want you to fill in yourself, or just rewrite the details, and there'll always be one or two pieces that I'm not going to do, otherwise there wouldn't be anything left, and so you'll see what I mean. Okay, so here is this function. Let me draw the graph of it. There's t, and there's little f sub x of t. And notice that I always use t as the independent or dummy variable instead of x, like in ordinary calculus. And the reason for that is that I use x here which is traditional in probability, as the name of a generic random variable. Now, typically, the name of the random variable is an uppercase X, and the values that the random variable takes is a lowercase x. In a textbook, that's okay. You can differentiate by the type font, whether it's uppercase or lowercase. But in a lecture, if you have to keep on saying big X, little x, you forget those things, the x's get confused. When I write, if I were to write a little x here, a lowercase x, and uppercase x, half the time you couldn't tell the difference. When you write it in your notes, you won't be able to tell the difference, so it gets confusing. So I just always call my independent variable a lowercase t, and I reserve uppercase x for the name of the random variable, which is irrelevant at this moment, and I rarely use a lowercase x. Okay, so that's the dummy variable or independent variable t. That's the function, and this is its definition. So here is 0, here's 1, here's 1. So if I draw the graph, it would look like this. 0 for t negative, then 1 for t between 0 and 1, then 0 for t greater than 1. That would be the graph. Now, what's difficult about this, such as it is that when you plug into formulas like this, the problem is that the function that fits in here is only, simplest possible thing, either 0 or 1. But whether it's 0 or 1 depends on its argument. So for example, as the u moves between minus and plus infinity, this piece right here is 0 except when u happens to lie between 0 and 1. And then the function is 1. But when u lies between 0 and 1, t minus u could be any value depending on the value of t. And so different values of t are going to make a difference whether what fits in here is either that or that or that. And of course that makes a difference in the answer, because the answer depends on t. So in freshman type calculus, what they usually do is you have something like this. So you'll have, let's say, a sine wave. So maybe it'll look like this. That's more complicated than this, but the simplicity of this is that it goes on forever. You don't have to worry about changing the formula based on where the variable is. But in reality, you often have, because remember this is supposed to be realistic, so this is describing real functions, things that you would measure. So what this says is that this thing is defined only within a certain region to be non-zero, and every place else it's 0. If I ignore the fact that the function has 3 different formulas for it, one definition but 3 different formulas, then of course everything's going to get screwed up. So this is much more realistic than something that has the same form and goes on forever between plus and minus infinity, at least for certain kinds of applications. So in that sense, this is more difficult because it has 3 branches. But each branch is as simple as you can get, a constant, either 0, 1, or 0. So this is what causes the difficulty. So when people say that, ask me whether they should go back and study their freshman calculus, my answer is usually no, until you've looked at this and have a more of a focus on what it is you're studying in your freshman calculus. But if you just look at the whole subject, the chances are you're not going to see the parts that I'm interested in. Okay, so this is a typical kind of function, and it's defined, it's very simple, but it has 3 different branches or 3 different formulas that define it in 3 different regions. Now the other function looks like this. This is the second density function. And by the way, this density function describes the random number generator in the computer. The question?
This GT, which we are evaluating, is as we are obtaining it from the integration, so it is a basically continuous function.
The G is a continuous function, yes.
Yes, so if it is a continuous function, should we join the curve, right, which is going from 1, so we should also join it by a vertical line in the graph?
Wait, this is not a continuous function. But when you draw the graph, as this is defined, it looks like this. It's defined here and here. Now, when you draw it, it's often easier to see with the eye if you make some kind of line like that. So that's fine with me. In fact, I prefer that. It's easier to see. If it's continuous, which this isn't, but if it is, then of course it doesn't matter.
So we can join it with the line if we want.
Yes, yeah, that's the way I would draw the graph.
What I
Yes.
think he's trying to say is that that jump with 0 to 1, you do have that instantaneous continuous delta function. So you can find that delta function, you get a straight line. So instead of putting the dotted or dashed lines, you should have, there's one above the other. It's a discontinuous drop. He's thinking along the lines of the delta function. So you got this.
Okay, the delta function, for most people this is a confusion. In fact, delta functions are used in, say, electrical engineering and physics. Mathematicians don't like them because a delta function really isn't a function. But for our purposes, I think just like convolution, if I were you, I would forget about delta functions. Okay. You don't need to know anything except simply working directly from the definitions here. So this is a function that's completely well defined. It's just a discontinuous function. It helps to draw the line in here, the vertical line, because it helps your eye, but the vertical line doesn't mean anything in terms of the value of the function, because when t is equal to 1, the value of the function is 1. When t is equal to 0, the value of the function is 1. So it's not something in between, it's not something higher, it's 0, 1, and then 0. So if you already know about delta functions and you think that's helpful, that's fine. But for all of you who never heard of delta functions, flush it from your brain. It's not going to be any help. Okay, the next function. The next function is in some sense simpler, but in some sense more difficult. It's simpler because it has only 2 branches, but it's more difficult because it's not a constant in both those branches. So this function is 0 when t is negative, and it's lambda e to the minus lambda t when t is not negative. So this is your standard exponential function. The lambda is a positive constant. It can be any positive constant. And in this case, what I'm asking you is to take lambda equals 2 when you actually make numerical calculations. Now if you draw the graph of that, this is a sketch. It'll look something like this. Here is the function, f sub x of t. Here's t. It's 0 when t is negative. Then it has a discontinuity, and when t is equal to 0, you jump from this branch to this branch. And the value, when t is equal to 0, is lambda. In your case, that's 2. And then if you plot it, that is, you take different values of t, you plug them in here, you calculate this formula, and then you plot its graph, and then connect the points, it'll look like that. Now, what you have to do is you have to actually plot the points. So you know it's going to look something like that, but there are different ways to draw a shape that looks like that. I could draw it like this, I could draw it like this. It's important that you actually have the correct numerical values in it. This is what you use a calculator for. So it turns out, surprising to me, that there are always some students who don't know how to draw a graph, which is kind of amazing if you're talking about senior level students in College of Engineering, but somehow or other it always happens. So for most of you this should be easy, but if you don't know how to draw a graph, then now's the time to learn. Okay, so these are the 2 functions I'm going to be concerned with, and although you don't have to know that now, let me just state what they mean. This is the density function, which describes the randomness of the random variable x when x represents the random number generator in the computer. Or equivalently, if I were to take this little dial and spin it, this is 0, that's 1, and pick out a number at random, then this function right here describes that randomness, as we'll see later in the course. Now, this also describes something that's very fundamental. This describes the randomness of events occurring with complete randomness in time or space. In other words, suppose that I imagined a process like this. This is time 0, and every once in a while something happens. Like, for example, a Geiger counter clicks. That's a standard example that people use. So let those arrows represent the times at which you hear the Geiger counter click. And then it turns out that this density function describes the times between the arrows. So in fact, we're going to be using this to describe the times in which messages occur generated at random in the internet going to a channel for transmission to the next stage. That'll be our engineering application. Okay, so these are the two functions, and then it asks you to calculate some stuff. So I got to erase this. Okay, so there's case number 1. That's this one. And then it asks you to calculate E of x, which will turn out to be the average, E of x squared, which will turn out to be related to how variable the random variable is, capital F, which is the distribution function, because here what I'm doing in the problem is I am specifying 1 and 2 by giving you their density functions. And then from that, you plug into the integral that I just erased. I'll write it again, and that gives you the distribution function. Now, as the problem is stated, it asks you to calculate g of t. I'm going to leave that blank for a moment, or move over to here. Here's g of t. And then it asks you to calculate the integral, or area under the curve, of g of t between a and b. So what this says is, you're going to use this formula here, and you're going to find out the formula for this function, then you're going to put that function in here and calculate this integral. It's easier than it looks, so don't worry about it yet. And here, what I'm going to do is I'm going to add a new piece. So this is not in the version that's on the website at the moment. And I'm going to make this, ask you to evaluate this integral between a and b of the density function, dt. Okay, so those are the pieces. So let me start and do this guy right here. Okay, so you want to calculate E of x, which by definition is the integral from minus to plus infinity of t times little f of t dt. Okay, so now I'm going to write this thing out in all its glory, even though ordinarily you wouldn't do that. Because what I recognize here is that little f has 3 different pieces to it. I'll draw it again here. So here is 0, here's 1, here's 1. So the graph looks like this. Now, this function right in here is 0 as long as t is negative. So what I want to do is I want to rewrite this, although ordinarily I wouldn't write all these terms. I'll write this as the integral from minus infinity to 0 of t fx of t dt plus the integral from 0 to 1 of t fx of t dt plus the integral from 1 to infinity of t fx of t dt. Remember that integral means area. So what this thing says is that I want to find the area between minus and plus infinity, so that'll be the sum of the areas between minus infinity and 0, 0 and 1, 1 and infinity. Now the reason I chose to break it up this way is because the f is given by a different formula in this region as it is in this region, in this region. Each of these regions has its own individual formula. So for this case, when t lies between minus infinity and 0, the function is 0. So this would be the integral from minus infinity to 0 of t times 0 dt, which of course is 0. in the interval between 0 and 1, little f is 1. So this would be the integral from 0 to 1 of t times 1 dt. In the interval between 1 and infinity, this function is 0, so this would be the integral from 1 to infinity of t times 0 dt. Now, ordinarily, I wouldn't write this, because it's just a lot of writing for nothing, but I'm trying to emphasize what I'm doing here. So this piece right here, because of that 0 in the integrand, that's 0. And similarly, that's 0. And so my answer is given by this, whatever that integral is. This is the only time here where I actually have to evaluate an integral. Okay, so let me do that. Let's see, we're always running out of space here. So I'm going to go here for the moment. So I'm evaluating this guy right here. So I've got the integral from 0 to 1 of t times 1, I don't need to write that, dt. Okay, now comes the calculus, and as you all know, to integrate this, I have to find the function whose derivative is t, so that would be t squared over 2. That's the fundamental theorem of calculus. I find the function whose derivative is the integrand, and then I evaluate it at the upper limit, the lower limit, and subtract it. And so when I evaluate it at the upper limit, I'm going to get 1 squared over 2. And when I evaluate at the lower limit, I'm going to get 0 squared over 2, which of course is 1 over 2, or 1/2. So the answer is 1/2. So in a sense, the calculus part, which is right here, that's the easiest part. There's nothing to that. The rest of it is easy too, but it's not easy in every possible case, as you'll see when we start looking at convolution. Okay, so that's the arithmetic. So what you should do is you should write something like this on your worksheet. But what I want to see when you turn it in is I want to see the 1/2 written right here in the table. So any questions about that? Now right now it doesn't mean anything. But remember, if you take my word for it, that what this density function describes is what I get, what the random number generator would give me, or what I would get, in fact, if I just chose a number at random between 0 and 1, then if E of x represents the average, which, again, we'll see later in the course, then you would expect that the average value of a random variable that is that lies between 0 and 1 and picks the values out at random ought to be in the middle, which is 1/2. So we'll see later that this makes sense as the model of the average. Okay on that? Okay, so now let's look at the next one. And now I don't have to go through that same detail again. I can say this. Now I want to calculate the expected value of x squared, which by definition is the integral from minus to plus infinity of t squared times the density function, dt. Of course, we know, just like before, that this f is 0, except when t is between 0 and 1. And when t is between 0 and 1, it's 1. So I can immediately rewrite this as the integral from 0 to 1 of t squared times 1 dt. And now when I integrate that, of course, I get t cubed over 3, evaluated between 0 and 1, and that answer is 1/3, so this answer is 1/3. Okay? Okay, let's look at capital F. So by definition, capital F is the integral from minus infinity to t of the density function evaluated at anything other than t, call it u, du. So this says find the area under little f between minus infinity and t. So let's draw a picture. Okay, so now, let me call the dummy variable u. So this is u, and this is f of u, and according to the formula, it would be 0 when u is negative, and then it would be 1 when u lies between 0 and 1, and then it would be 0 for u greater than 1. And I want to find, according to this is what it asked for. It says find the area under this function as u varies between minus infinity and t. So the answer is going to depend on where t is. It's going to be a function of t. So suppose that t is negative. Suppose I put the t right here. Then what this says is I want to find the area under this function as u varies between minus infinity and t. Of course, if t is negative, then the enclosed area is 0. So what I would say is this. Capital F sub x of t is equal to 0 if t is negative. If I were more formal about it, what I would do is I would be writing this thing, except that if the t is a negative number, the f that fits in here is 0. So since I'm integrating 0, then of course the answer is 0. So as long as t is negative, then big F is 0. It's going to have different branches depending on where t is. Suppose t lies between 0 and 1. So that's t. Get rid of this guy right here. Okay, now this area would be the area between minus infinity and 0, which is 0, plus the area between 0 and t. Okay, so now, let me just write it separately here. Okay, I'll write it over here. I have the integral up to 0, which is 0, and then I have the integral from 0 to t. And in that interval, the function f is 1. So it would be 1 du. So now I have to integrate 1 with respect to u. Of course, the answer is u, because u is the function whose derivative is 1. And then I evaluate it at the upper limit, the lower limit, and subtract it. Of course, when I do that, I get t minus 0 or t. So the answer is capital F is equal to t if t lies between 0 and 1. Now notice that this is obviously true. I don't need calculus to evaluate that, because what does this mean? This says take the area. So I want to take the area under this function for the dummy variable between 0 and t. So what I have is I have a rectangle. Its height is 1, its width is t, so its area is t. T times 1, that's the t. So if you remember that an integral is an area, you can often evaluate the areas that we're going to, or the integrals that we're going to have in this course, as long as the functions that we're integrating happen to be geometric, simple geometric functions. So if we're integrating constant, for example, then what you're calculating is the area of a rectangle. So we're going to be calculating areas of rectangles, triangles, things like that, because you don't need to actually use calculus in order to evaluate something like this. Okay, what about when t is greater than 1? So now suppose that t is over here. Okay, so now we want the area under this curve between minus infinity and t. Between minus infinity and 0, the area is 0. Between 0 and 1, the area is the area of that square. And between 1 and t, the additional area is 0. The total area is included between 0 and 1. So if t now is greater than 1, then the total area enclosed is going to be the total area under the function, or it's going to be 1, the area of that square. So f is equal to 1 when t is greater than 1. That's my answer. Okay, so I would write that here like this. Well, what I would do is I would simply take this statement and I would put it in here. Okay, so big F has 3 branches, 0, t, and 1. And then one of the questions is to draw its graph. Well, we've already drawn the graph of little f. There it is right there, or right here. What's the graph of big F? Well, it's given by this function. So, in fact, let me redraw little f. So, call that t, call that little f of t. It looks like this, 0, 1, 0. Now, big F, what does its graph look like? Here is big F. Here is 0, here's 1, here's the value 1. This graph is 0 when t is negative. Then it has the value t, capital F of t equals t. That's a straight line with a 45-degree slope. And then it's 1 for t greater than 1. That's 1 right here. So this point right here is 1. So this is the graph. That. Now notice that for any t, the height of this graph is the area to the left of t for that graph. So I imagine as my t moves from left to right, then as it moves, the cumulative area that's enclosed in the upper graph is the numerical value of the lower graph. So I start over here, I move from left to right, and as I move, the enclosed area is 0, 0, 0, and so forth. Then when I get to this point, it starts to increase linearly until I get to here, and then it remains constant because there's no new area that's added. So the height of this graph for any t is the area to the left of t in the graph above it. That's what integral means. Similarly, this is the derivative of that, and you can see that because the derivative of 0 is 0. The derivative of t, the slope here, is 1. The derivative of 1, slope there, is 0. So this graph and this graph are equivalent to each other. Of course, it's easy to see when you're talking about something as simple as this, but this is what you have to remember. So to draw the graph of this and the graph of this, you just use a little ruler and draw those straight lines. Okay, any questions about that? Yeah.
I don't follow how you got the 1 for t greater than 1.
Because this thing here, remember what the definition of this is. This says find the area under this function between minus infinity and t. So if t is greater than 1, over here, then the area between minus infinity and that is the total area that's enclosed, because the only time this function is not 0 is when t is between 0 and 1, or in this case, calling it u, when u is between 0 and 1. So once this t exceeds the value 1, once that t exceeds 1, the cumulative area never increases. It just remains constant at 1. Just this area of this box. Okay, so the fundamental theorem of calculus essentially is the relationship between the derivative and integral, right? This is the derivative of that, that is the integral of that. And integral is area. Okay, now the next piece, which is not on the version that's on the website at the moment, which I'm going to add, asks you to calculate the integral of the density function between a and b, and it says take a equal to 0.25 and b equal to 1.35. Okay, so let me get rid of this. Okay, so we're over here now. The integral between a and b of f of t to the left of t dt. That's the integral between 0.25 and 1.35 of f of t dt. Okay, now here is little f. Here is 0.25. And here is 1.35. So we want to find the area under this function between that value and that value. So obviously, I'm going to break this down into two parts again. First, I'll find the area between 0.25 and 1, because in that region, little f is 1. And then I'll find the area between 1 and 1.35, because in that region, the function is given by another formula, which in this case is 0. Of course, this integral is 0, and this integral right here, well, to integrate 1, I just get t. I evaluate it between 1 and 0.25, of course, gives me 0.75. Okay. But of course, that was easy. I didn't need all this calculus, because what this is saying is, find the area under this curve between 0.25 and 1.35. Well, that's the area I'm looking for, right there. And that's the area of a rectangle whose height is 1 and whose width is 0.75. So therefore, its integral, its area, would be 0.75. Okay, so this answer is 0.75. Okay? Okay, now the next part is to find g of t, and then to integrate that. The integration part is actually easy once you find g of t, because it'll turn out that g of t is again some kind of geometric figure, so you don't even need calculus in order to evaluate the integral. However, you have to figure out what g of t is. That means you have to take the function f, you got to put it in here, you got to evaluate this integral. So this is sort of difficult, or at least it's difficult for most people based on what they already know in calculus, because remember that when you plug the functions in here, you have to plug in the proper value for the function, and that value depends on the value that's inside these parentheses. If the value inside the parentheses lies between 0 and 1, then the function is 1. If the value inside the parentheses lies outside of that, then the function is 0. So as u varies between minus infinity, that thing moves and that thing moves. And when this one moves, the difficulty is that what you need to know is not just the value of u, but you need to know the value of t minus u. And you want to get this answer for every possible value of t. Because remember, all of these cases, when we get these functions, they have to be defined for all values of t. In some cases they're 0, in some cases they're not, but you have to know what that is. You can't just leave the 0 part out. So the difficulty here is knowing how to set this thing up. But once you know what the integrand is, then it's actually easy to evaluate, because the integrand is either 0 or 1. That's all it can possibly be. So let me skip that for the moment and go to case number 2. And it turns out that in some sense case number 2 is easier, because case number 2 has only 2 branches. But in some sense it's harder, because to actually evaluate the integrals you've got to use calculus, because this isn't a simple geometric figure. Okay, so I'm going to skip this for the moment and go to case number 2. Any questions so far? Yes.
We evaluated for t equal to 1.25.
Say it again.
At the very bottom, we evaluated for t.
Right.
What are the two numbers again?
This should be 7.5. 7.5 here. Okay. This says that when I integrate this, I want to find the function whose derivative is 1. Well, t, derivative of t is 1. Derivative with respect to t. So by calculus, I replace that 1 by a t, and then I take that answer and I evaluate it at the upper limit, which is 1, and the lower limit, which is 0.25, and I subtract them. So this is 1 minus 0.25, which is 0.75. Okay? But now I'm pointing out over here that I didn't really need calculus in order to do that, because all this is saying is find the area under the rectangle whose height is 1 between 0.25 and 1. So that's this area right here. So since integrals are areas, if the function whose area I'm trying to find happens to be a simple geometric one, then I don't need calculus to figure out what its area is. But if the curve here that represents the function is not a simple geometric one, then I need calculus. Okay, so far I haven't needed calculus in order to actually evaluate any of these integrals. Because even when I had a t or t in there, that's actually a straight line. That area is the area under a triangle. Again, I learned how to do that in like 9th grade or so without calculus. That's just the area of a triangle. So I didn't need calculus in order to evaluate this stuff. Okay, so now I want to do the same thing for case number 2, and now the function is given by this, and this is not just an arbitrarily defined function whose purpose is to annoy you. This actually, we'll see, is very important in applications, because just as we'll see, this function describes randomness in the sense that if I pick out a point in a finite interval in such a way that all the infinite points that are there are equally likely to be picked, then this turns out to be the density function. And this thing says, if I just imagine that events are occurring randomly in time, and a good example of that is radioactive decay, so every once in a while, for no apparent reason, some fundamental particle, electron or something, will decay, and then it'll register a click on a Geiger counter. So we imagine then that at time 0 we start listening, and every instant is just as likely as any other instant to have a click. And if I do that, I'm going to have these series of clicks which will run from 0 to as long as I want to listen. And the question then is, how can I describe this random process? Because not only does it describe clicks of a Geiger counter, which measure radioactive decay, but it describes anything in which you can imagine that events occur randomly in time, and every instant in time is as likely to give you a click as any other one. So it doesn't matter whether this thing is radioactive decay or a message arriving at a channel in the internet, or a telephone call arriving at a switchboard, or an accident on I-95. You could look at each of those things as being a random event that occurs in time, and then it will turn out that the random variable, the randomness, describes the times between those points, has this as its density function. And the only thing that changes from one application to another is the numerical value of lambda, which is just a parameter, which we'll see later what that means. Okay, so now we're going to look at this, and we're going to make the same calculations for this. This is called the uniform density function, by the way. This is called exponential. Okay, so now let's look at case number 2. So the first question is to calculate the expected value. So the expected value of x is equal to the integral, this is the definition, from minus to plus infinity of t times density function of t dt. And now I've got to plug this function into this integral. This is going to be the integral. Now, this function has 2 branches. When t is negative, it's 0. When t is not negative, it's lambda e to the minus lambda t. So immediately, I can start the integral at 0 and run from 0 to infinity, because between minus infinity and 0, this function is 0, so the integral is 0. Between 0 and infinity, the function is lambda e to the minus lambda t. Okay, so now I have to integrate this. And this is the only time when the tricks of calculus are necessary in order to evaluate the integral. So I'm going to tell you how to do it, but it's not important except that you understand what you're doing, that you're evaluating an integral. But in order to do this, you have to integrate by parts. This is one of the tricks that you learn in freshman calculus. But that doesn't mean you have to be an expert on integrating by parts, because in this course, this is essentially the only time this is going to happen. But when I evaluate this integral, so I'll just say like this. I'm going to write here, by parts. Okay. When you do that, the answer turns out to be equal to 1 over lambda. Okay, so what do you do in your homework? There are several possibilities. You could refer to a textbook that shows this as an example, because it turns out that since this is so important and so simple in terms of an example that illustrates the notion of integrating by parts, it's in just about every textbook. So if you were to say, this is in a textbook, in fact it's in our textbook, on page such and such, I don't know what page that is, but so you have to look up the page. But if you were to say that, and the answer turns out to be 1 over lambda, that's okay. If you had software that was smart enough, or a calculator that's smart enough to evaluate this integral, the answer would turn out to be 1 over lambda. You could just say that, if you had it, if you just say what it is you're using. When I went to school, we didn't have calculators. We had handbooks. You could look this up in a handbook of integrals, and you'd say this is integral 728 on page 52 of Burrington's tables, and the answer is 1 over lambda. Or you could actually work it out just as if it were a freshman calculus problem, integrating by parts. But no matter how you do it, the answer is going to turn out to be 1 over lambda. Okay. So what I wanted you to write was 1 over lambda. Now later on, you'll see the meaning of this, because remember I said that this represents the average value. And so the parameter that appears in this formula is the reciprocal of the average length of the times between those arrows. Again, this is stuff that comes later in the course. That's the purpose of the course. Okay, so this will turn out to be 1 over lambda. Okay, so we should fill in something, right? If you just write exactly this, that's not enough. But you have to write a little bit more than that. The best thing, of course, is to actually evaluate this integral by parts. That will, I think, make you feel better because it'll connect you with something you think you know. Of course, you really don't, because you don't know why integration by parts works. All you do is just replace one level of ignorance with another, but it gets to the point where there's a certain level of ignorance which you were taught. The earlier you were taught it, the more willing you are to accept it, even though you have no idea what it means, and you can base the rest of your life on it, right? Like everybody knows that if you multiply a negative number times a negative number, the answer is positive. And everybody will fight to the death to defend that position. But I wonder how many people can tell me why that's true. I mean, the whole idea doesn't make any sense. What does it mean to take something that's negative and multiply it a negative number of times? I have no idea what that means. And I don't think anybody else does. Is that right? Anybody want to explain why -1 times -1 is +1? But if they teach you that in 7th grade, that's it. You know it's true. Okay, so if it turns out it's not true, what that means is that the world will spin apart, electrons will become positive, whatever that means. So your whole life is lived based on these facts that you were taught as a child, that you have no idea why they're true and may not be. You don't want to find that out until you die, maybe. Okay, suppose you want to calculate the expected value of x squared. So from the definition, using this definition, I would get the integral from 0 to infinity of t squared lambda e to the minus lambda t dt. And now again, integrating by parts, it will turn out that the answer is 2 over lambda squared. Okay, how about capital F? Let me go over here and do that over here. Capital F is equal to, by definition, it's the integral from minus infinity to t of the density function evaluated at u du. In other words, it's the area to the left of t in this curve. So in fact, here's a picture. Here is the density function. So this is little f. Let me call it u. And so I want to find the area under this curve between minus infinity and t. So first of all, suppose that t is negative. Suppose t is over here. Well, obviously the answer is 0, because this function, defined right here, except that here, of course, I'm calling the argument u, there I'm calling it t. You have to be able to go back and forth between these things, because when I'm looking at this in isolation, I like to use t as the generic dummy variable. But when it's plugged into another formula and I want to use a t as generic independent variable there, I have to change the name here. So I want to find the area under this function to the left of t. And that means that I'm integrating this function for u now negative, which means from minus infinity to t, where the u is negative. So of course it's 0, just like before. So this answer is going to be 0 if t is a negative number. Okay, now suppose t isn't a negative number. Then the picture would look like this. There's t. And now we want to find this area right here. So this is equal to the integral from 0 to t of lambda e to the minus lambda u du. And now it's standard calculus. Remember that the exponential is the function whose derivative is itself. That's why it appears all the time in engineering and physics and applied mathematics. So that means that when I integrate this, what I'm going to get is minus e to the minus lambda u, evaluated between 0 and t. Right, if I differentiate that thing right there with respect to u, the minus lambda comes out here, multiplies, that's the lambda, and the minus signs cancel, because a minus times a minus is a plus for a reason that nobody has the foggiest idea. And then I plug in the values, and when I plug in the t, I get minus e to the minus lambda t. When I plug in the 0, I get 1. Minus times a minus cancels, again, for reasons that nobody has any idea. And the answer turns out to be that. So in other words, this is the answer, 1 minus e to the minus lambda t, if t is greater than or equal to 0. So going back over to here, then what I would write in here is this. Okay. So here all I did was draw an arrow showing what's supposed to go here. Here I'll write it. So what I would write is fx of t equals 0 if t is negative, and 1 minus e to the minus lambda t if t is not negative. So going back over to here, let me erase this. If I draw the graph of little f, as we saw, it looks like this. Big F, remember, is the integral, or the area under little f. And as we just saw, the answer right here is 0 if t is negative, and 1 minus e to the minus lambda t if t is not negative. So if I draw this graph here, then I get 0, and then if this is the value 1, drawing the graph of that gives me a curve that starts at 0 and is asymptotic to 1. Again, you have to plot this. That is, on a calculator, you have to plug in values of t and plug them into here, get the numerical values, plot the points, connect them. Because when you plot the points, you should do it in a way that you can't see the points. So those are only your guide. So it might look like this. But you don't want to see those points when you're done. Because remember that you're plotting the graph for all t. Of course, you can't plot it for all t because there's an uncountably infinite number of points. So you pick some, and then you connect the curve. But this is what the thing should look like. And of course, although you can't see it as clearly here as you could before, the derivative of this is this, and the cumulative area under this curve is that height. Okay, so that gives you this piece right here. The next thing is you want to evaluate, let's see, I think I can get rid of this. You want to evaluate the integral between a and b of the density function, dt. So this is the density function. So if I call this u, well, let me leave it as it is. This is the density function. I want to evaluate the integral between a and b. In our case, a is 0.25, and b is 1.35. Is that right? Are those the numbers I said? Okay, that's another point, by the way, is that this problem, actually I've used this before, because obviously it's a good problem, it gets right to the heart of things. But each semester when I use it, I change the parameter values of A and B. So don't fall in the trap of handing in a paper whose answer is the answer for the parameter values that I used last semester. That's the trap. So don't anybody fall in it. Don't even look at old homework problems. All right, so I want to find this area right here. So in other words, this is the integral from 0.25 to 1.35, and in that region, the function is given by this formula right here. So this is lambda e to the minus lambda t dt. Okay, so I can evaluate this integral because I already did that. I did that in general, and then when it was called u, and it integrated between 0 and t. So I don't have to integrate again. In fact, if I use the fundamental theorem of calculus, I know that since capital F is the integral, I could write it this way. I could say that's the same thing as capital F evaluated at 1.35, because remember, I've already done this integration, minus capital F evaluated at 0.25. Or in other words, it's equal to 1 minus e to the minus, I'm evaluating this thing here. Now lambda is 2, because I said that when you evaluate the integrals numerically with a and b, I want you to take the value lambda is equal to 2. Similarly over here, when you draw this graph, you have to pick a numerical value of lambda, so I'm saying use lambda equals 2. So then this thing would become e to the minus 2 times 1.35 minus 1 minus e to the minus 2 times 0.25. And so you just do that in your calculator, whatever that turns out to be, gives you some answer, a number. Okay, so that's what you put here, whatever that number is. Of course, here you actually had to use a calculator to get this. Now, you could do it two ways. For example, I didn't have to get this thing, integrate it, and then put this in the calculator. If I had a calculator that evaluates integrals numerically, all I have to do is tell the calculator, this will work with like a TI-89 or TI-83, all I have to do is tell the calculator the integrand, the variable, the name of the variable of integration, and the limits, and press the button, and it'll tell me exactly what the answer is, which is really a nicer way to do it. Okay, so that gets you here. So where we are now is we've got to look at convolution, and we've got 15 seconds left, so I can't talk fast enough to do that in 15 seconds, so we'll do that next Thursday. Any questions before we quit? Okay, so I'll see you Thursday.